Okay, so it's Sunday afternoon. Made a lot of progress over the week and just want to sort of recap where things stand with the high precision GPS disciplined oscillator. So this is the new version. It's been reduced. I'm only capturing the 1 byte of the count 'cause I only really need 5 digits of that. And I've done some changes to the display. But under here is the oscillator, and that's being held in this foam, which keeps it thermally stable. That's the GPS. This is the latch. This is the counter. This is the Arduino. Then these are the controls, up, down, and so forth. And so this is a simplification and a lot more robust than the old version, which was just on the breadboard with the cheesy jumper wires. So this thing, don't breathe on it. You're going to mess something up. But now I got this a lot more stable, and I made some changes to the display here. I've limited how many digits I show of the current sample count, what the difference is, and then what the error is. And then in parentheses here, this is how long. In this case, if it's been 0 for a while, this tells you how long it's been 0 and what the deviation was of the last error. So the fact that it's a plus here means it was +1 at some point, and it's been that way for 22 seconds. And then below it is what the last one was. So this way you don't have to keep on looking at it. So say I see that's running fast now, so I can just reduce the DAC control word by 1, and hopefully it'll make the run go longer. But even at 25, as it's 25 seconds between errors, that's 4 parts per billion, and I've gotten this to be, I think, 300. So that's 300 parts per trillion. So it's 27. So I know I need to slow it down just a little bit more. And then that's the temperature. The temperature seems to be way off. It's not 12 degrees in here. It's more like it should be more like 20. But that's just this temperature sensor over here. And I was going to put it close to the can to know what the temperature is of the oscillator, just to know when it's okay to start taking readings. But as it turns out, the error count is good enough, and it's stable enough, so that's not really that critical. And so I'm still adjusting this. And I haven't done anything with the automation to make it work manually, to make it work automatically. And I'm sort of happy right now just being able to tweak it, because actually having this figure out over a long run which way to go and making it smart, and then to not see the slip where it does like a +1, -1, +1. That's a lot of software work, and I'm kind of not up for that. I'd rather work on the hardware for now, and then once it's in a box and it's just programming stuff, maybe I'll do that. But it's been running very well. Of course, I don't have any of the glitches like I had before, because I have a shorter word that I'm looking at. And then I'm happy with the performance. Just having it be, this is 32 seconds. That's sort of approaching maybe my target. I know with just the right combination, letting this warm up enough that it can run for a long time. And so let's move this off to the side real quick. And so this is the final block diagram of the circuitry to do the counting. So I have the clock coming in from the oscillator can, and that goes through an inverter. This is 3.5 volts coming out, or 3.3 volts coming out. And so if I go through this inverter, it makes it a solid 5. So all the logic's good. And one copy of that drives some flip-flops, which gets used coming out of the PPS, and the PPS and the GPS. It aligns the PPS signal with the clock edge, which I'll explain on this tiring diagram underneath the board there. And that is what gets used to latch the count every second. And the clock coming out gets used to drive the counters, which is just the lower 8 bits. And then when the PPS comes by, I latch it, and then it goes into this I/O expander, and then the Arduino can go read that out via I2C. And the Arduino knows to read that out because it sees the PPS and it can sample that. And so when it sees the PPS come by, it knows there's a new value to go get. So the tricky part of this design is the fact that the PPS is asynchronous to the clock. And so it went up to 30, so it's 18 right now. I'll just move this aside so I can work on showing what happens. So this is a timing diagram. I haven't done one of these in a long time. This is the 10 megahertz clock. And so, and you know, there's an inverter here, but that doesn't really matter. In the end, it goes up and down. This is, you know, time across this aspect. The problem is the PPS signal, I'm not sure when it comes in relationship to this edge. And the danger is if I just sample it and use that value, what comes out, it's not exact. It's metastable. It's metastable potentially. And so what metastability is if I have a signal, this is a D, and I have a Q, which is the output. This is my clock. And so the idea here is I want to capture what D is and put it on the Q clock output. So when a clock edge comes, there's a concept, there's a setup time and a hold time relative to the data you're sampling. So here's the data edge. I'm sampling, it has to be a little bit before and a little bit after when that edge actually comes. And if I do that, there's a small propagation delay from this edge to where it actually shows up on the output. So see, there's a small difference there. But key to this is the setup time and the hold time. If I were to sample the data without enough setup time, what shows up in the output might start to go up and never quite make it there and go back down. And as I increase the setup time in relation to the edge, there's a chance that that edge could come up, you know, even more and still not make it. And if I have, you know, setup and hold time kind of mixed together and maybe I just make it, it might take a long time to rise up because inside, even though this is digital logic, the circuit is still analog and there's feedback and so forth. And so the fact that when I clock this edge without sufficient setup and hold time, there's a delay in this Q. If I use this Q for other things, like clocking this logic device, stuff inside this may interpret this as occurring at different times. And so you don't want to do that. So that's what's shown here is that when I do a PPS and I sample it, the PPS coming out, which is here. So this is a flip-flop. So the purpose of flip-flop is whatever, when the edge comes here, I take whatever's on the input and it goes to the output. This first one, PPS 1, may have a little bit of instability in it if this edge isn't well placed. I clock it again, you know, 100 nanoseconds later, because that's the time between the clock edges here. That one for sure meets a setup and hold time. So if I have this situation where the rising edge is taking a long time, it's going to be stable by the time the next clock comes in. So it's just a standard synchronization circuit. So from this, I get a PPS2, which is what I use to latch the latch, which captures the data at the current count so that the CPU can read it with the I/O expander. When this edge occurs, the latch signal has a little bit of propagation delay, so it's not perfectly aligned with that edge, but it happens after. The other thing that happens is the counter uses a negative edge, so it doesn't count on the upgoing clock, it changes on the falling edge. And I have a inverter here to invert that for a delay element, but I'll explain that here. So here's the 10 megahertz coming in. Here's the clock that I'm actually using to trigger the counters. And so the count changes when this edge goes down. And the output of this counter, there's 8 bits, Q0 through Q7. And the way this counter works, if you look at the data sheet, here's the clock coming in, and every time this goes up, it toggles the value. So it'll be 0, clock comes in, it goes to 1, Another clock comes in, it goes back to 0. And this edge is used to clock the next stage, and that edge is used to clock the next stage, and so forth. So this is a ripple counter. And so when the edge comes here, if this changes, that makes this change. If that changes, that makes this change. So there's a delay between each of the bits moving through the device, as opposed to a synchronous counter where they figure out what it's supposed to be and then they change it at the next edge. So shown here, here's the clock edge coming down, and the count changes. So if the count was one thing here, where these X's are, it's going to be then valid till the next edge. And there's a little bit of delay. It's 16 nanoseconds is what I measure, which is what the typical value is. And then each subsequent bit will change a little bit later. So the 8th bit, Q7, it changes later because it takes time to ripple through the counter. So it changes out here someplace. And what I want to make sure of is that if this bit changes first and this one takes a while, that the thing actually latch the value in happens at the right time. So here is the first bit changing, second bit changing. So the last bit changing. So the last bit is stable here. And as shown in this quanta of time, that lines up. Here's the latch signal. That latch signal occurs in the middle after the bit has been stable. And then once it's been stable, the output of this latch gets fed to the I/O expander, and that's what's shown here. So I latch it here. The data is valid a little bit later, and so this time period, all the way until the next second, the data is valid, and that's how long the Arduino has to come around and actually read it out. So what this shows is that I avoid any kind of timing glitch. The problem I worried about is if I had multiple bits coming into into these latches, by the time the last bit changes, you could already be starting to change the first bit. And so this is 100 nanosecond time. I think the delay from each stage, I think it might have been 4 nanoseconds. And so, if it's 24 bits, it'll take 96 nanoseconds, which is almost the time for the next clock edge. So that's maybe what I was seeing when it was glitching. I was just on the edge here. So I avoid that problem by only looking at some of the bits, and I only need to look at some of the bits because I'm not trying to capture a large error. And so I'll show on my counter here the last one was 55 seconds slow that it went, and so that's 2 parts per billion. And then I just knocked up the control word a little bit, so this is increasing even more. So that shows the stability of this device. So that's kind of where things. Let's let it count some more. So that sort of shows you where things stand. Again, I was happy I have a nice, solid with the thermal isolation system. There's less noise in the design, and this is going to make it to 100. So I guess I'll risk it and move it back. See, it has less. There's less noise. I have more bypass caps kind of everywhere. I bypassed all these devices, and even though I can measure noise, and then also the power for the oscillator goes through these filters and nothing else touches it. And so it should have a clean supply. And there's noise in there, but that noise, even though it theoretically a voltage offset will affect the frequency, it's constant, and whatever electronics is in there is only seeing the average value of that noise, which is the 5 volts that's going in. And you can see now that I moved it, it doesn't. It's not as stable. And I think that if I tap it, I think I can. See now, yeah. So now it's positive a lot. So it's changed a little bit because there's this crystal in there that's oscillating or resonating at a certain frequency, and the mechanical stress on it matters. I think if I press on it, it will Yeah, see, it changed. It again, that thermal, that mechanical stress on it had it change its frequency. So now it's running slow again. So you can speed it up a little bit. That shows you how sensitive that is. And again, we're dealing with parts per billion. So like I said, it's a quarter inch over 3,000 miles is the accuracy that I'm achieving here. So that's where things stand. I think the next step, I haven't really talked about the digital synthesizer to make the frequency out based upon this clock. But right now, this clock is kind of junky. I'm not sure how good it's going to be for this chip. I bought some chips that came in. It's a tiny, tiny, tiny little package. I have to somehow solder it to a board to be able to use. So we'll see how that goes. And I might work on maybe trying to get an auto tuning algorithm plugged in here so I can flip the switch and have it tune. But happy with the progress, happy with the accuracy. I need to talk about how this actually gets used with the radio and then compare it to the store-bought one. But that'll be for a different video. Anyway, thanks for watching.